Hi, hello. Welcome to my channel, Dr. V.I.K. Reddy. Today I will be covering Fourier series, that is in continuation to the previous lecture part 1. Today I will be discussing even and odd functions, how to write the Fourier series for even and odd functions. Let me take you to the examples. The part 1 lecture I have given introduction to even and odd functions. Again, we will recall those definitions. A function is said to be even if it is satisfying f of minus x is equal to f of x. We call the function as even function. Whenever f of minus x is equal to minus f of x, we call that function as odd function. And examples for even functions is f of x equal to x square. So here you are replacing x by minus x and the output also x by minus x, that leads to x square. That is the same function like f of x original function. Hence you call it f of x equal to x square is a even function. And f of x equal to cos x also, you replace f of x by minus x. Similarly, the output is cos x. So there also you have to replace x by minus x. Cos minus x is cos x. Therefore, you are getting exactly f of x. These are the examples of even functions, and you can generate many more. Let's say that x power 4, x square plus x4 and x into x square into cos x etc. You can define many more. And similarly, if you look at the definition of odd function, it is f of minus x, that is whatever the x values are there, independent variable, you replace that independent variable by minus x based on the function output. Here the output is minus x is going to x cube, therefore minus x must be like minus x cube. So 3 minus signs are there, 2 minus signs will give you plus and another minus sign will give you minus x cube, that is minus of f of x. Hence you are concluding that this is an example of odd function. Similarly, you can say sin x, f of minus x is equal to sin minus x, that is equal to, so sin of minus x is equal to minus of sin x. The sin x is the original function, therefore you are writing this is exactly equal to minus of f of x. Hence you are able to show that f of minus x is equal to minus f of x. Therefore that is the odd function. Now you can play with them. So some of the even functions are odd functions. So examples are something like some of the even functions, x square plus x power 4, x square minus 2x power 4, or x square plus cos x, or secant x plus 5 into x square plus 10 into cos x. All these are additionals. I mean, you are applying operator addition over these even functions. Output is an even function. Similarly, if you look at addition of odd functions, So addition of odd function is again x cube x. So if you add these two, it is again, if you add x cube plus x, these two are odd functions, therefore output is again odd function. So sin x plus 10x, these are odd functions again, minus 10 sin x plus x cube plus 100x, all these are the odd functions. Therefore addition of an even function, addition of even functions gives you an even function, addition of odd functions will give you odd function. So now what about the product or the multiplication? So whenever you pick it, x into x cube, this is x power 4, the simplest example. So this is giving, so multiplication of odd into odd, odd times odd gives even function, even times even gives even. So mixed functions. So even times odd is equal to odd function. X square into sine x. This is x square sine x is odd function. X square is even, this is odd, therefore product is odd. Similarly, odd into even. This is again odd function. So whenever you see the multiplication, in the process of multiplication, whenever you have different type of functions, one is even, another one is odd, the output is always odd function. So x power 4 into x cube is x power 7, or x power 1 into x square is equal to x cube is again odd. These are the examples of odd functions, and we can generate many such examples. Of course, that is not our task to go on. So I will take you to the Fourier series. We will apply, we will find Fourier series of a function, even or odd function, okay, over the interval minus L to L type. We are finding Fourier series of f of x equal to x over the interval minus pi to pi. So you observe this, f of x is equal to x is odd function. Odd function, and it is defined from minus pi to pi. Therefore, we can use the property of the odd function since it is defined from minus pi to pi. Therefore, you can conclude that a0 is 0, an is 0. You can test it by defining, by calculating a0 and an also, you will be getting 0. So suppose a0 you want to find 1 by L c to c plus 2L f of x dx. So you compare c to c plus 2L with minus pi to pi. So if you compare, c is equal to minus pi, c plus 2L is equal to pi. Therefore, minus pi plus 2L is equal to pi implies 2L is equal to 2 pi, L is equal to pi. So therefore, a naught is equal to 1 by pi minus pi to pi x dx 1 by pi x square by 2 minus pi to pi, and that is equal to 1 by pi times into 1 by 2 times pi square minus of minus pi whole square is equal to 1 by 2 pi times pi square minus pi square, which is 0. So similarly, you are getting 1 by L times c to c plus 2L f of x sin x sin n pi x by L dx, which is equal to 1 by pi integration minus pi to pi, and f of x is what? F of x is equal to x sin n pi x by pi, L is pi dx, which is equal to 1 by pi minus pi to pi and x sin nx dx, which is equal to 1 by pi times which is equal to 1 by pi times x integration sin nx dx and minus pi to pi. The lower limit is integration minus pi to pi d by dx of x integration sin nx dx into dx. Now you simplify, this is equal to 1 by pi times x minus cos nx by n minus pi to pi and minus 1 by pi. This is minus pi to pi integration. Derivative of x is 1. Derivative of sin x is minus cos nx by n dx is minus cos nx by n dx. And further, if you simplify, this is equal to, and now you substitute upper limit and lower limit. This is pi cos n pi minus pi of cos n into minus pi and minus 1 by pi. This minus and this is becoming plus, and then integration minus pi to pi cos nx dx. This is equal to minus 1 by n pi and 2 pi cos n pi plus 1 by n pi times 1 by n into sine nx minus pi to pi. So, in both the cases sine n pi, here sine n pi or sine minus n pi, both are 0. This is 0, this is 0. So, hence you have only first term, that is minus 1 by n pi, of course 2 pi, pi cancels, and cos n pi, which is equal to minus 2 by n. Cos n pi is minus 1 whole power n, because cos n pi value is minus 1 when n is equal to 1, when n is equal to 2 cos 2 pi, that is 1, when n is equal to 3 cos 3 pi is minus 1, and so on and so on and so on. So, and so on. Therefore, your answer is, that is x, Fourier series of x over the interval, it is a naught by 2 plus summation n is equal to 1 to infinity a n cos n pi x by L plus b n sin n pi x by L when L is equal to pi, it is equal to a naught is 0 plus summation n is equal to 1 to infinity a n is 0 cos n pi x by pi plus b n sin n pi x by pi, pi cancels, pi cancels, which is equal series of, therefore Fourier series of x is equal to summation n is equal to 1 to infinity, and we should have b n value. B n is minus 1 whole power n plus 1, 2 by n, and multiplied with sin n x. That's it. This is the Fourier series expansion of f of x equal to x. Now, so find the Fourier series expansion of f of x equal to x square over the interval minus pi to pi. So, since solution, since the interval is pi to pi, that is symmetric about origin. Along x-axis, therefore, and further f of x is even, f of x is equal to, further f of x is equal to x square is an even function. Therefore, bn's must be 0. So, now our task is to calculate a0 and an only. What about a0? a0 is equal to 1 by L c to c plus 2L f of x dx. But c comma c plus 2L is equivalent to minus pi to pi. I mean, we are equating to get it L value and all. Therefore, c is equal to minus pi, c plus 2L is equal to pi, and minus pi plus 2L is equal to pi, 2L is equal to 2 pi, and then L is equal to pi. Therefore, this is equal to a naught is equal to 1 by pi minus pi to pi, f of x is x square dx, which is equal to 1 by pi, the integration of x square is x cube by 3 and minus pi to pi, which is equal to 1 by 3 pi and pi cube minus of minus pi whole cube, which is equal to 1 by 3 pi, pi cube, and minus times minus pi cube, that is 1 by 3 pi, 2 pi cube, which is equal to 2 by 3 pi square, that is a naught value. Now we have to calculate an value. To calculate an value, we have to use the definition. An is equal to 1 by L C to C plus 2L f of x cos n pi x by L dx. But C is equal to minus pi, C plus 2L is equal to pi, L is equal to pi. By substituting all these values in an, we will be getting minus pi to pi, f of x is equal to x square, and cos n pi x by pi dx. Pi cancels, which is equal to 1 by pi minus pi to pi x square cos nx dx. Since it is a second degree polynomial in the integrand, we have to split that into the three times, three parts, three terms we are going to get in the expansion. In the first term, we are going to get it x square, you are retaining, applying the integration over cos nx dx minus pi to pi minus 1 by pi integration minus pi to pi derivative of x square into integration of cos nx dx that is 1 by pi into x square. Integration of sin cos nx is sin nx divided by n minus pi to pi minus 1 by pi integration minus pi to pi. Derivative of x square is 2x and integration of cos nx is sin nx divided by n into dx. If you substitute here, the first term is going to be pi times sin n pi minus of minus pi times sin minus n pi minus 2 by pi integration minus pi to pi x sin nx dx. And here you see sin n pi is 0, sin of minus n pi you can write it as minus sin n pi, but sin n pi is again 0. Therefore, your output is reduces to minus 2 by n pi minus pi to pi x sin nx dx. Again, this is a first degree polynomial is there. We have to apply by parts. In the by parts, integration by parts, we have to differentiate x. Therefore, x is becoming constant next time and no need to bother about those terms. Integrand, you can easily apply the integration over the rest of the term. Therefore, I am writing this minus 2 by n pi, and if you expand x into integration sin nx dx minus pi to pi minus 2 by n pi integration minus pi to pi d by dx of x, derivative of x, since we have left over the x without doing anything, now we are applying derivative integration sin nx dx into dx. Now, in the first case, if you look at that, the upper limit and lower limit sorry, in the first case, it is, if you try to simplify, this is minus 2 by n pi into integration of sin nx is minus cos nx divided by n and minus pi to pi, minus into minus is plus 2 by n pi and minus pi to pi, derivative of x is 1, sin nx integration is minus cos nx by n dx. Now, this is equal to, again if you try to substitute lower and upper limit, that is going to be, I am taking this minus outside first and this n is also outside, that is 2 by n square pi and then x cos nx minus pi to pi. So, this is minus 2 by n square pi integration minus pi to pi cos nx dx. Now, if you try to simplify further, that is 2 by n square pi and upper limit is pi cos n pi minus of minus pi into cos minus n pi, and the other integral is, so you apply integration over sin cos nx that is sine nx by n integration from minus pi to pi. Here the both upper limit and lower limit are appearing in the form of sine nx n pi, sine n pi and sine minus of n pi, but all are 0. Therefore, this entire term is nullified or ignored, which is equal to 2 by n square pi, and this is pi times cos n pi minus plus pi times cos minus n pi. This is equal to 2 pi by n square pi 2 cos n pi, which is equal to 4 by n square into cos n pi is 4 by n square into minus 1 whole power n plus n whole power n. So it is valid for n is equal to 1 onwards, n is equal to 1, n is equal to 2, n is equal to 3 for all integers. Therefore, this is the output of f of x equal to x square over the interval minus pi to pi. Fourier series of f of x over this interval. So, how do you do that? Well, it is very simple. Since f of x is equal to x plus x square, this is odd over odd function over minus pi to pi, and this is even function over minus pi to pi. So, what I am going to do is that this f of x I am going to write it as sum of two functions h of x. So, what is the advantage of this one? Suppose you are trying to solve this problem. Suppose you try to solve directly. Then you have to calculate a0, an and bn as f of x is neither odd nor even over minus pi to pi. So, it is tedious to calculate a0 is equal to 1 by L C2 C plus 2L f of x dx. If we compare, we have seen that it is 1 by pi minus pi to pi, and then f of x is something like x plus x square dx. Of course, this is handy to you, but what about an? Calculate an. Since a naught is directly related with polynomial integration is easy to handle. You don't see the difficulty. Why splitting is more important here. Now, while calculating an and bn, you will understand what is the advantage of splitting that given function as two parts. So, why did I mention that the splitting is more important? You can see now. So, an is equal to 1 by L c to c plus 2L f of x cos n pi x by L dx. But pi L is pi, therefore minus pi to pi, f of x is x plus x square cos n pi x by pi dx. This is equal to 1 by pi times minus pi to pi x cos nx dx and plus 1 by pi minus pi to pi x square cos nx dx. And this is the term which is going to be 0 and which you are calculating unnecessarily. Anyway, so this is actually tedious. Unnecessarily we are increasing the length of the problem. Similarly, if you look at this, bn is equal to 1 by pi minus pi to pi and f of x is x plus x square sine n pi x by L, but L is pi, therefore here you observe that minus pi to pi x sine nx dx plus 1 by pi minus pi to pi x square sine nx dx. This term we are calculating unnecessarily. We are calculating as this term is going to be 0. So that can be reduced by writing f of x is equal to g of x plus h of x, as g of x is equal to x and h of x is equal to x square. Then so you look at that, now you are taking g of x is equal to x is an odd function, h of x is equal to x square is an even function. Now you know that for g of x only bn is needed, bn survives, therefore bn is equal to 1, you are only calculating minus pi to pi, g of x is x sine nx dx. That's why I told you this is unnecessary calculation. And similarly, if you look at that a for f h of x is equal to x square, which is an even function, therefore Fourier series of h of x is equal a naught survives, bn is equal to 0 by default. So here in the calculation of an, it is 1 by L minus pi to pi f of h of x cos n pi x by pi, L is pi, therefore 1 by pi minus pi to pi, and h of x is x square cos nx dx. You see here in an only you need to calculate x square into cos nx. That's why I told you this is unnecessary calculation. So you can save time by splitting that into the two parts and you are able to manage it. And ultimately at the end we are writing f of x is equal to a naught by 2 plus summation n is equal to 1 to infinity an cos n pi x by L plus bn sin n pi x by L dx. So for these functions, for the function defined over minus pi to pi, you can say that symmetric about the origin along the x-axis. There is a symmetry minus a to a. For these intervals it is valid. Otherwise you cannot use. Suppose x equal to x square over the interval 0 to pi. Here you have to, here we should not apply the technique that is even or odd. Suppose f of x equal to x square over the interval 0 to pi, then here we should not apply the technique that we learned above, that is we should not use the technique learned above, that is f of x equal to x square is even function and but you should not shouldn't calculate a0 an alone. There may be a contribution from bn which may not be 0, as the function is defined over 0 to pi, not over the interval, well, minus pi to pi or minus a to a. So there is a difference. We cannot apply just like that. For this, we have to follow the standard procedure. That is, let me solve this problem as well. That is, a0 is equal to 1 by L c to c plus 2L f of x into dx. But c plus 2L we have to compare with 0 to pi. Therefore, c is 0, 0 plus 2L is equal to pi, L is equal to pi by 2. Therefore, you are getting a0 is equal to 1 by pi by 2, 0 to pi, f of x is x square dx, that is equal to 2 by pi, x square integration is x cube by 3, 0 to pi. Therefore, it is 2 by pi, pi cube by 3, which is equal to 2 pi square by 3 is a0 value. Similarly, you have to calculate an is equal to 1 by pi by 2, 0 to pi, f of x cos n pi x by L, L is pi by 2 dx, which is equal to 2 by pi, 0 to pi, f of x is x square and cos 2n pi, 2nx dx. You have to apply the bipartition technique here. That is, x square integration of cos 2nx is sine 2nx by 2n 0 to pi minus 2 by pi integration 0 to pi. Derivative of x square is 2x and integration of cos 2nx is sine 2nx divided by 2n into dx. You see here, this value, whether you substitute x equal to pi, sine 2n pi is the one case, sine 0 is the n into 0 is the other case. In both the cases, this is 0. Therefore, x square is non-zero in the upper limit, though it is pi square times sine 2n pi, but sine 2n pi is 0. Anyways, in the lower limit, x square itself is 0. Therefore, you are getting both the terms are 0 in the first case. What about this term further if you try to expand it? That is equal to minus 4 by pi into 2n and 0 to pi x sine 2nx dx is the leftover term. Now, if you try to simplify, this is equal to minus 2 by n pi and integration of this is there. Again, we are using by parts. First is x, integration of sine 2nx is minus cos 2nx divided by 2n and upper limit is pi, lower limit is 0, minus 2 by minus of minus 2 by pi, 2 by ns cos 2nx by 2n dx, and this leads to again you look at this, minus into minus is plus 2 by 4 pi n pi, this is n pi into 2n and upper limit is pi cos 2n pi minus lower limit is 0 into cos 0. And similarly here, if you take this negative here, this is minus 2 by 2n square pi integration 0 to pi cos 2nx dx. So this is equal to 2 1 this one 2 cancels, therefore that is 1 by n square pi. In the numerator, if you look at that, pi cos 2n pi, cos 2n pi is always 1, therefore pi minus 0, lower limit is 0, this is 1, this is equal to 1 and this is 0, this is 0. And moving back to this one, minus of course 1 by n square pi and 0 to pi cos 2nx dx, but this output is something like sine 2nx by 2n and when you apply 0 to pi, the sine 0 is 0, sine 0 2n pi is 0, sine 0 is also 2n into 0 is also 0. Therefore, this is actually 0. So, which implies pi by n square, pi which is equal to 1 by n square. Similarly, you have to calculate Bn value, like 1 by pi by 2, L is pi by 2, the integration is 0 to pi, and f of x is like x square, and sine n pi x by pi by 2 dx, which is equal to 2 by pi and 0 to pi x square sine 2n x dx. And if you try to simplify, this is 2 by pi x square minus cos 2n x divided by 2n, upper limit is, lower limit is 0, upper limit is pi, pi, and the other bipartition is 2 by pi times 0 to pi, x square differentiation is 2x, derivative of sine 2nx dx and dx. This is going to be 2 by pi, minus I am taking out, therefore, and 2n also I am taking out. This is upper limit, if you substitute, pi square cos 2n pi minus 0 square cos 0 square cos 0. So, therefore, only survival term is this one, and then minus 4 by pi into 0 to pi x into cos, of course, minus sign, minus cos 2n x by 2n dx. This you can rewrite it as minus pi square by n pi minus into 4 by pi 0 to pi, and this is 2n also, you can bring it out, x cos 2n x dx. Now you have to further simplify. First step, it is becoming in the integration x sine n 2n pi x 2n pi, sorry, 2nx divided by 2n, but upper limit is 0, pi, lower limit is 0. In all those cases, 2n, in all those cases, you will be getting 2n pi, sine 2n pi or sine 0, all are 0. In the second case, you will be having minus 2 by n pi into integration 0 to pi. Derivative of integration of cos is sine 2nx divided by 2n dx, and this you further simplify, this is 2 by n pi into 2n into integration of sine is minus cos 2nx divided by 2n. Of course, here the limits are from 0 to pi, therefore cos 2nx 2n pi minus cos 0 is going to be 0. Therefore, this term also no contribution. Only survival term is of the form minus pi by n, that is the Bn. Therefore, now you might have noticed that whenever the interval is not in the form of, whenever the interval is not symmetric about the origin along x-axis, we cannot neglect a0, an, bn, despite f of x is even or odd function. Yeah. Thanks for watching. In the next video, we will learn how to express the piecewise functions in the form of Fourier sine and cosine terms as a linear combination of sine and cosine terms. Thank you.